Good morning to everyone. I'm Dr. Sumi MS. The topic of my today's presentation is static registers and latches from Unit 3 Sequential Logic Circuits and Clocking Strategies. On completion, the students will be able to define bistability principle and also understand about the SR and D flip-flops implementation. The bistability principle. Static memories use positive feedback to create a bistable circuit. A bistable circuit has two stable states that represent 0 and 1. The basic idea is shown in the following diagram, which shows two inverters that are connected in cascade. The output of the second inverter is connected to the input of the first inverter, and this is represented using dotted lines in the following diagram, and the resulting circuit has only three possible operation points, A, B and C, where A and B are the stable operation points and C is the metastable operation point. This diagram represents two cascaded inverters along with their voltage transfer characteristics, where for inverter 1 we are giving input VI1. Following that, the VO1, which is the output of inverter 1, is given as input to inverter 2 as VI2, and VO2, which is the output of inverter 2, is given as input to inverter 1. This cross-coupled inverter pair is biased at a point C, which is the meta-stable state. It is amplified and regenerated around the circuit loop, and this bias point moves away from C until one of the other operating points A or B is being reached. The C is an unstable operation point. Every deviation crosses the operation point to run away from its original bias, and the operation points with this property are termed to be as metastable. Set reset SR flip-flop implementation. This circuit is similar to the cross-coupled inverter pair, with NOR gates being replaced at the inverters. The second input of the NOR gate is connected to the trigger inputs S and R, thus make it possible to force the outputs Q and Q bar. These outputs are complementary except for the condition S and R as 1. When both S and R are 0, the flip-flop is in quiescent state and both outputs retain their value. If a positive 1 pulse is applied to S, then the Q output is forced to the state 1 with Q bar going to 0. Similarly, when 1 pulse is applied on R, it resets the flip-flop and Q output goes to 0. But when both S and R are high, both Q and Q bar are forced to 0, which is considered to be as a forbidden mode. So this diagram represents the schematic diagram of SR using two NOR gates along with its characteristics table. We can also obtain a SR flip-flop using cross-coupled NAND gate structure. Clocked SR flip-flop. Clocked SR flip-flop is a level-sensitive positive latch. It consists of a cross-coupled inverter pair along with 4 extra transistors to drive the flip-flop from one state to another and to provide a clock operation. Consider the case when Q is high and R pulses being applied. The combination of these transistors M4, M7 and M8 form a ratioed inverter, and in order to make the latch switch, we must succeed in bringing Q below the switching threshold of the inverter. Once this is achieved, the positive feedback causes the flip-flop to invert states. This requirement forces to increase the size of the transistors M5, M6, M7 and M8. So this diagram represents a clocked SR flip-flop. And this is SR latch with NAND gates. D-latch. One way to eliminate the undesirable indeterminate state in the SR flip-flop is to ensure that both the inputs S and R are never 1 simultaneously. This can be obtained by converting it into a D-latch. Quiz questions on static registers and latches. write about SR flip-flop implementation. Thank you.